Good day, everybody. I'm John Clark. I'm the Professor of Computer and Information Security at the University of Sheffield, but for the purposes of today, I'm the Principal Investigator of Pitch-In. So welcome to our conference, Successful Innovation in the Internet of Things. A few preliminaries for you. Some technical info, so we would advise you to stay muted until you're invited to speak, and if you don't, the hosts are going to do it for you. So, we have a fairly authoritarian view of how to control meetings with probably over 100 people attending. We're going to be recording today's event, so if you object to having your interactions recorded, please don't interact because we will be recording these. If you want closed captioning, you can actually click on the appropriate buttons as you see there on the right. And actually, you can find out actually who else is here. So you can type you can edit your name to include your affiliation. And we're going to be using extensively the chat. So if you have questions throughout the day, please put them in the chat. And the speakers, because of the speed we're actually going to deliver some of this stuff up, may not have time to respond to them in the talks. But they will be able to answer them if you put them in the chat. But why not use the chat buttons and tell everybody who you are and what you do, etc., and introduce yourself. So, right. Now, what to expect this morning? This is the timetable. You'll have seen it in the agenda on the Eventbrite. I'm going to be giving a brief overview, not a detailed one, a brief overview. We've got a number of project highlights from 10 o'clock to 10:50. A half-hour break. We know Zoom meetings or online meetings can be a bit taxing, so we put in a significant break here. More project highlights later on from 11:20 to 12 o'clock. And then we have something from the KTN, and which is Richard Foggy and Sylvia Liu, who are going to be talking about 5G and the IoT. I'm going to be talking later on about towards connected resilient society, which is really where we are going. And then we're going to have a question and answer session. We'll have a chat storm, and I'm going to be posing some questions to you, and we'll be taking anybody present from Pitch, and we'll be taking questions afterwards, and we can have a discussion as well. So I think that's it. So I'm going to press ahead. Oh, sorry. A word from our sponsors. Research England, as part of the Connecting Capability Fund. So the Connecting Capability Fund is a way of funding what's described here as HEIs funding. This is infrastructure funding, which is awarded to universities, but these are competitive. So we had to compete to actually get the funding to do this. The aim is to show good practice and capacity internally across higher education sector and elsewhere, in fact, forge external technological, industrial, regional partnerships and deliver the government's industrial strategy priorities. And those loom large. We're one of 18 projects. We received £4.93 million of funding and about £4 million in leveraged funding, incidentally, from our supporters. If you want more details on the Research England CCF program, the Connecting Capability Fund program, look actually at this link. These slides will go online after the event today, so you'll be able to access the links. Right, so what I'm going to do is look at Pitch-In, promoting the Internet of Things via collaboration between HEIs and Industry. Pitch-In's a much more manageable name for us, really, but that's its origins. I'm going to be giving a little bit of a program overview, and I'll say I'm not going to go into details. Left to my own devices, I'm a security and safety specialist, high integrity software specialist, essentially, but today I'm here as principal investigator for the PI for the consortium. So the Pitch-In vision, I'll just briefly outline what we wanted to do was to show how the universities, together with our partners, industrial, commercial, and third sector partners for that matter, could deliver benefits by significantly enhancing Internet of Things innovation. So we're really about innovation in IoT, getting the stuff out there, getting research adopted, making a difference to people's lives, and importantly, ensuring that the right sort of tech actually is delivered. So building strong relationships and IoT innovation ecosystems, the ecosystem becomes very important, where universities and industry play their full part. The ecosystem will sustain beyond the life of the project, and including alignment with the Made Smarter and other initiatives, actually. So we have a particular emphasis, as you'll see, on technical, social, managerial, and organizational barriers to innovation in IT, both for our stakeholders, the barriers they face, but also what the barriers we face internally operating as universities. We are concentrating on manufacturing, energy, cities, and health and well-being. But also there's a meta strand, which is the less techie one, which is the social sciences in IoT. It's not all about the tech, and that'll come across strongly as we go through the day. We're going to address issues that apply across all sectors, and we're there to support the industrial strategies you'll see shortly. And if you wanted a strap line for what we do, it's making value apparent, because if value is apparent, people will take stuff up in IoT and indeed elsewhere. It's not just the industrial strategy. The industrial strategy gives rise to some grand challenges, and we support some of those as well. Some aims: look at the barriers and opportunities to exploit and develop IoT, and then to disseminate results. To contribute to the development of regional ecosystems. These are tremendously important, as we've actually begun to appreciate more than we did at the time when we got the funding. To demonstrate benefits to business. So I say our strapline is making value apparent, and so demonstration will crop up repeatedly during my talk, especially, and during the day, actually. And actually, so to develop a means for universities to fully exploit their capabilities. Where do we fit in as universities? What can we do that we do best or are very well suited to? And what do we lead to other people? And where do we meet with those other people to actually provide a better and more significant offering? To act as a springboard for further collaboration activities, we have about 12 or 13 follow-on grants, which have actually proposals which have followed on from with the people working in Pitch In. And to capture and exchange knowledge, and that knowledge could be to enhance sustainable value, and that could be methods, new models, new methods, new business models, for example, and actually new tools and techniques and mechanisms as well. I won't go into a great deal of detail, but you see our themes here: manufacturing, health and well-being, energy, smart cities, and one at the top, which is management. And management ended up being also dealing with the non-techie stuff, essentially, much of the non-techie stuff, and the cross-sector stuff as well. Down below, we see the regional ecosystem, which is where the universities commissioned their own projects actually for their own local needs. Now, we commissioned probably, sounds a bit odd, but yeah, 70 mini projects, or actually over 70 mini projects. We won't report under 70 mini projects. Some of those may be combined, but there were a very wide range across all these things you actually see here. Most projects were bottom up. We asked for help to address a number of barriers. We identified a number of barriers to start us off, but we allowed people to sort of say, well, actually, these are important barriers for our stakeholders or us. And so we actually had a good deal of most projects were bottom up. The regional engagement ones, because they had to cross sectors, those were actually commissioned by local and managed by local management, essentially. All of these were, or pretty much all of these were collaborative. Certainly all the bottom-up projects were collaborative, and many of the regional engagement projects were collaborative as well. We committed to 70% or so to have at least one university, industrial, government, or similar external stakeholder. Virtually all of a great many of them, way in excess of 70%, actually were collaborative. We just worried too much when we were agreeing our KPIs. So here are some themes and lessons. And I'm going to mix these two. I'm not going to go into detail again. You'll see many of these lessons emerge later. So support for the industrial strategy, you'll recall, or if you're not, you'll now be aware of, there was an industrial strategy building a Britain fit for the future. And that was a white paper published a few years ago, which gave rise to these grand challenges of artificial intelligence data, which we certainly hit, aging society, which we hit via the Health and Wellbeing strand, clean growth and clean energy use, which we hit major, and the future of mobility, we addressed a little bit. Our proposal was against the green paper, and the green paper was more eclectic in its needs. Okay, the industrial strategy tends to focus on manufacturing processes, and also clean energy. Who are the gas guzzlers? Who are the real heavyweight electricity users? Now, can you reduce that? Our program was actually proposed and delivered against the previous version, which was the green paper. So you can look these up on these websites given with the links here. Making value apparent. So what on earth can academics do to make value apparent? Well, we can engage in a variety of ways, actually. So we've got here engaged at a fundamental level as to what value in IoT consists. For example, development of mechanism evaluation frameworks here for mass customization via the internet. I first came across this research at Cambridge, and that was one of their projects that went ahead. I've since come across it elsewhere. This is really ahead of the game. This is a big interest. Development of general technical or even cross-domain. Actually, this is something academics do rather well at, because they tend to solve, if they can solve one problem, they try to solve more than one problem, and hence actually developing generic technology which has cross-sector appeal and deployment is the sort of thing which we are likely to do as academics more than people in a particular sector actually addressing those particular sector needs. Leveraging IP, this is a project that really excited me, which is if you've got IP embedded in a system, how do you actually make money from it and leverage the IP you have when it's only part of a bigger system? You'll see a talk later today from Cambridge. All sites did demonstrations. Demonstration is big, and that was emphasized by across the universities. So demonstrations loom large, demonstration looms large in all the technical themes. So the Made Smarter report, a great report incidentally, about digitizing Britain and the prospects for it and how to do it, did emphasize the role of demonstrators and demonstrators in the catapults. And these were largely large-scale demonstrators. We believe there's a great role to have for demonstrators at various smaller scales. So in manufacturing, you'll see later on, low-cost demonstrations at trade fairs were absolutely great, and were a great way of actually just getting interest in what Cambridge did here. Cambridge did an awful lot of work in the manufacturing theme and led it. Energy, you'll see demonstration software, experimental systems later in the talk. Cities have engaged in demonstrations in a major fashion and at scale via our pitch in support for the Urban Flows Network, and that's Sheffield and Newcastle. And health have been able to demonstrate capability at scale on real people with real problems, and that's just one of the ways we can engage with the ecosystem and our friends, big organizations typically, to solve problems and demonstrate the value of IoT. Skills, a number of things. I won't go into a great deal of detail, but the point here is going down the left, these are the things we actually did. The light blue is Sheffield, the red here is Cambridge, the green is actually Siemens, and the digital catapult is Discovery Program is in black. We basically realize the importance of skills and of complementing other initiatives. So what's on the right are existing initiatives. I'll be talking about this particularly later. So we've developed skills and training courses to actually deliver and benefit from for the community, but also as actually as a way of gaining an introduction, an entree, if you like, to various people who need training and what their problems are. That's why major reason why we actually did it. I'll talk about this later. Leveraging our own specialist skills. This is one of the surprising outcomes, actually. So research software engineering is now a path in academia. You can actually have a career developing software for disciplines and communities. This was highlighted. Now, the Research Software Engineering Scheme is sponsored in particular by our Research Council, Primary Engineering Research Council, Engineering and Physical Sciences Research Council, EPSRC. And this was particularly appreciated by the Oxford energy researchers, but actually these issues resonate widely. So there are significant opportunities to engage fully with research software engineering for a number of reasons. Engineering research specialists aren't necessarily software specialists, and I'm afraid sometimes it shows, and sometimes it shows very badly. Developing credible and professional looking software facilitates impact and engagement with stakeholders. It's just much better if you have something that they would recognize as something they would want to look at and believe. We ought to train, incidentally, as a lesson, our research staff and PhD students much better, because you can't always get the software developed for you, but software is so intrinsic to actually an awful lot of what we do in research, we really ought to be concerned about the quality of that software. And software integrity has become a major issue as a result of the COVID-19 pandemic and the work that had to be done on the simulation software for COVID-19 spread, epidemiological spread modeling, in order to make it publicly releasable. It was actually, frankly, a bit of an embarrassment. So research software engineering IoT, combining both IT user interfacing and all the rest of it with real-time expertise is a real possibility. Low cost. Low cost has emerged as a significant enabler. You're going to see low-cost manufacturing from Cambridge later, but it's been seen across the project. So Oxford, for example, came up with what I've described elsewhere as Flash IoT, rapid demonstration of value by getting cheap sensors in to get some data of adequate quality. The full IoT can come later. This has occurred elsewhere as well. And actually, I just looked around today. If you look elsewhere, Cambridge Consultants announcing the lowest cost IoT network technology around. Its interest elsewhere, the Digital Catapult has an interest in low cost too. It's a major enabler, and Cambridge in particular are at the forefront of this. Dealing with legacy systems. Okay, so first catch your IoT system, then build it. Well, no. If we digitize in Britain, no one's going to redesign their whole plant in order to facilitate our IoT research or potential innovations. But dealing with legacy systems is essential, and dealing with it effectively is really a significant opportunity for us. So there are some significant issues, incidentally. We'll deal with parts of this later on in the talks. Security is still a big issue. We did one demonstrator to show how a 1970s lathe, which was at the AMRC, we got HEIs to actually build a security demonstrator to ensure the communications could be achieved with such an old bit of kit. So there are very significant investments in urban sensing. It's not going to go away. We're going to have to use that. The question is, how do we actually secure that appropriately and things like this? And the various cities initiatives are attempting to leverage this. So legacy is important. Also important, incidentally, is not creating a nasty legacy. HEIs have sort of suggested that sensors may be the asbestos of the future. They're littered all over the place. Dealing with real systems. So there's nothing more convincing than a demonstration that you can solve a real problem. So demonstrators in cities habitually deal with city data. So control for Newcastle city centre traffic is actually in the urban sciences building. That's close integration, and it's indicative of the closeness of the relationship they actually have with their city. Our urban observatory, similarly in Sheffield, has access to sensing across Sheffield and is actually helping with the IoT and LoRaWAN gateways and RF infrastructure. Health projects have leveraged connections with the NHS to demonstrate tangible benefits to end users with follow-on work. And it's important because if you're dealing with health, there are often restrictions, significant and actually quite appropriate restrictions on what you can do with data and the care you need to take, and the regulatory background actually kicks in. Work with Tinsley Bridge demonstrated, this is a manufacturing patent actually local to Sheffield, demonstrate how benefits of remote management and operation could apply to a working system. Dealing with real systems really matters. Of course, these require functional and fully functional and trusting relationships to be built up. And they generate problems, I'm afraid. So what you do find at times is that working available sensing technology and infrastructure can be found to be lacking. So environmentally hazardous environments, for example, and here I'm in the countryside, we need to be protected against the environment because it actually eats up sensors and causes them to malfunction in some cases if they're in remote parts and it's very rainy and all the rest of it. Things like GDPR can kick in. So security and privacy issues raise significant points. Incidentally, it's unclear how many smart buildings have had a GDPR audit. We are pursuing that sort of avenue. It does force the issues many times. And this applies, incidentally, when we look at universities, when we, for want of a better phrase, are eating our own dog food. Because when we think about our own infrastructure and control information, we feel it very deeply. And we have hit, even internally, and universities might have, we have 60,000, 65,000 students in Sheffield, for example. That's not unrepresentative. There are 2 universities, etc. There's a lot of data, and the universities are big organizations. New business models. It's not all about the tech. That's very, very clear. So let's take some from Cambridge in particular, exploring value via mass customization of products, new ways to demonstrate value and to create value and show how IoT can deliver it. That was facilitated by a pitching project. Leveraging IP or making money from IP. This crosses sectors, and you're going to see some more later on today on that. Also, local energy systems. We're moving away from national grids, the big grid. Well, not quite. The big grid will always exist, but we're actually looking to facilitate the use of more regional energy systems for sustainability and how they interact. That raises a number of additional issues with respect to actually what the business model is for those sorts of things. Building and supporting regional ecosystems, communications, you're going to hear later on from Newcastle in particular, but this is felt actually in several sites, meetups, real and virtual, newsletters, etc. All really important and very successful, both for education and actually just meeting people and understanding what people's problems are. And that's critically important. Leveraging and building on existing relationships, we've actually deepened some relationships, and part of the reason for that is that there was just such good material to work with initially. We wanted to deepen that, and that's part of the strategic directions of the university. Engaging entrepreneurs in mentoring, we got local people in to mentor the interns. In fact, interns themselves across sites actually were really, really productive at incredibly low cost, about 5,000 quid a shot or something, or even less in some cases. They managed to deliver over 12 weeks or something. Significant software, significant benefits, significant exemplars, etc. And the thing I would stress, incidentally, which we didn't really envisage, is that intra-university relationships were also benefited by the whole pitching process. Having that magnitude of funding and presence and profile actually enabled the internal researchers in the universities to make contact, and much has actually followed on from just actually knowing people in your own university better. So real esprit de corps has emerged across the universities, and new projects have actually been developed. Dealing with pandemics, move online to everything. Industry, several staff had to deal with other things, for example, the COVID response. Industry was also simply preoccupied, and we sought to achieve our aims in different ways. The word pivot increased in use, and that's all I'll say. Yeah. But there's also opportunities. COVID and general health has emerged, certainly at these three sites in particular. Remote operation and management, particularly Cambridge and Sheffield, and Cambridge are very big in this. Emerging supply chains, particularly at Cambridge in that case. Health and wellbeing more generally, and the importance of the environment, either urban, rural, and green spaces. It's all become more important, and IoT can help in those. So the pandemic itself, in a variety of ways, some of which were very unexpected, has led to more IoT opportunities for us. Build back better. I'm going to talk about that later on in sustainable connected society. Leveraging what exists, we made a ploy of seeing what we had available and seeing how we could support it and leverage it. So existing and continuing projects, significantly boosting impact and demonstration capability on available research. Okay, so here we have digital manufacturing on the shoestring, or IoT on the shoestring, as we often refer to it. Cambridge project, we essentially acted as an impact and demonstration arm on that. Urban flows. Both Newcastle and Sheffield are part of the Urban Flows Observatory, and so we are able to leverage massive existing infrastructure and relationships in order to actually try addressing some of the concerns. Building relationships with major players. In Sheffield, on our doorstep, we have Factory 2050 and the AMRC, part of the High Value Manufacturing Catapult. We've made contacts with the Digital Catapult. Siemens have sponsored the Mindsphere Laboratory at Newcastle, and also the Mindsphere Lounge, which is essentially infrastructure space and parts of equipment to actually do demonstrations and engage people in the communities in IoT. The reach of the catapults is huge. The influence people like Siemens can exert is very, very significant indeed. They sponsor research at several sites, but also they can facilitate introductions, and we leverage that on many occasions. Co-creation. So this slide here comes from a blog by Alice Frost of Research England, and the bit I really want to draw attention to is co-creation, because co-creation, as is appreciated in this blog, is the bit that tends to get less attention. There's been a lot of stuff on pull and push, but the genuine co-creation and co-development is one that is least well developed. We're going to be trialing manufacturing-oriented proposals writing in September. This is really building in stakeholder engagement right from the start, and so we'll be trying that as a proposals writing course in September. So co-creation in various ways was emphasized across all universities and all the sectors. It's of major importance in the health sector and always has been. Truly developing tech to serve users' needs is paramount and difficult. For example, if you're working with vulnerable stakeholders, actually engaging them to understand what their attitudes towards IoT and tech is difficult. And we have, in fact, developed some techniques for actually engaging with people with mental health issues, for example, just to understand better, because there's nothing worse than forcing tech from an academic's brain on an unsuspecting public, etc. It just doesn't work. Development of benchmark data sets, more data sharing, so there are opportunities and need for benchmark data sets. The need to build credible data sets and facilitate sharing on a principled and informed basis. And there's potential to build international collaborations on data set creation. So that's actually come out, particularly the international element, has come out of the energy. And you're going to hear a little bit from later on from Oxford about protocols and things like this. So it facilitates research, but it also enhances innovation capability, as I indicated earlier, demonstration validation purposes. Climate gate avoidance, I hinted earlier about software integrity. Well, actually, the protocols, actually what you've done with data is important. Cleansing, for data cleansing is a perfectly acceptable procedure to go through, but you need to come clear about what you've done, and that needs to be open to challenge itself. So the climate gate, I think there were 7 different procedures which have been applied to the data. The usual tricks, as somebody unfortunately mentioned in an email. Oxford in particular have been leading an effort to actually develop protocols for data management, essentially, and you'll see about that later. There's a clear desire across all sites to promote development of infrastructure to facilitate regional and wider data sharing. One pitching project has got 100K external support for this. Can't say exactly who is funding that, but that's true. All 4 sites are looking to further the living lab concept. Now, that was initiated by Oxford, but all sites buy into that, and we're looking how to take it forward. What I've described here is urban sprawl and seepage of expertise. Seepage expertise is, I think, a different concept. Okay, right. Expertise was deployed in new environments. So urban expertise from cities, particularly Newcastle in this case, was deployed in rural settings in the Slope Riot project, which was looking at detecting tremors and landslides in rural environments, etc. Oxford are also branching out into green spaces. So we started with our core themes, our core expertise, and things have branched out. Some further information, there'll be about 15 plus papers will emerge from Pitchin's efforts. The leverage contributions, the support we've had from the community and our friends, etc., has been significantly in excess of what we committed to. We thought it would be about 4 million. It's probably going to be in excess of that. It will be in excess of that, in fact. There's information available online at the following links. These slides will go up afterwards, so you'll be able to actually access these links and look more into it. So there are the 4 theme events here: health and wellbeing, energy, write-up and video, smart cities, and manufacturing. These are 4 single theme, single sector things that events we've actually held. Or you can view the videos directly on our YouTube channel, which you'll be able to follow the link here. And if I'm not mistaken, it's 10 o'clock exactly, and that's when we were meant to finish. So let's have a look. The first speaker today, who's going first? Sorry. If you could take the screen.
Hi, I think it's me.
Hi, Alexandra. Welcome. Hi, Alexandra. Take it away for your 10 minutes.
So I hope you can see my screen. Somebody nod, please. Thank you. Okay, so hi everyone. I'm Alexandra Bintrup. I'm from the University of Cambridge. I've been leading the manufacturing theme at our site, which was very much in collaboration with all the other university sites. So, so it was very exciting. My main research interests are AI in manufacturing and supply chains, which we have used also in this particular strands, which I'll talk about a little bit. So, so I'll be talking to you about really low-cost solutions in digital manufacturing. It has been a team effort, I must emphasize. So primarily led by Professor Duncan McFarlane and his team. So let me just go through and explain a little bit about pitching manufacturing in general. So as IoT is a vital enabler of Industry 4.0, pitching manufacturing strands specifically explored manufacturing. And by manufacturing, we not only mean factory operations, but also supply chains, logistics, engineering assets, and also innovation management. So low-cost solutions formed a key aspect to encouraging take-up in our work, the aim of which was to translate IoT research into manufacturing and supply chain applications and foster collaboration between universities and industry, but also within universities. So we have had to date about 18 mini projects out of the 70 that John mentioned earlier. So these projects lasted anywhere between 3 months to 2 years. And 12 of these were in Cambridge, 6 were in Oxford and Sheffield. So the vast majority of these projects were collaborative, and they included multiple universities and industrial partners. I think also, just to emphasize, as John mentioned earlier, that we followed really a semi-emergent approach in that we had an inclination of what sort of barriers and topics might be of interest. But we let researchers and industry come together and decide what was of primary importance to them. So in the end, our kind of post-hoc analysis showed that 4 main clusters emerged within the manufacturing strand, and low cost was a key priority one. So the challenge that we have been trying to address here with multiple mini projects was to foster the digitalization of information and automation systems. And we wanted to do so by making low-cost digital technologies available that are not necessarily industrial. So what we've been trying to examine is how we go about integrating non-industrial low-cost technologies to develop new solutions or enhance existing capabilities for a manufacturing operation. And the operation itself could be factory-based or supply chain-based. We looked at cloud-based control in real-time systems and also how machine learning algorithms could be used, for instance, for process improvement. Specifically, we wanted to build demonstrators because very early on, what we found out was that when we talked to companies about digitalization and IoT, particularly SMEs, about notions of digitally improving operations, the message got through a lot easier if we used a demonstrator. So whether it was about automating visual inspections, remote operations, condition monitoring, or even supply chain data integration, a demonstrator approach has been very helpful to create a momentum in this area. So just to give you an idea of our collaborative landscape, so we have had many SME manufacturers, as well as global engineering firms. I'm sure you can recognize some of the firms here. But we also tried to bring everyone together. So it was SMEs bringing them together with engineering firms and service providers, startups, as well as research centers such as the AMRC. So unsurprisingly, we kind of centered around our local areas. So primarily around the Midlands and the Southeast, but that was because we had a local engagement and ecosystem building objective, but we also generally had wider participation. So let me go through some of the activities to exemplify the approaches that were developed as part of the low-cost strand of Pigeon. So this particular example, low-cost production environment monitoring, is about gearing up a production environment to be able to communicate with sensors and other information to a programmable logic controller. In this case, we used the Beckhoff PLC. So this was really an enabling digital capability in that once we create an enabler of getting sensor data from processes, then that can lead on to other use cases such as process monitoring and improvement. So in fact, it was the result of a hackathon where we invited students to solve a particular set of challenges posed by an industrial consortium, and I'll talk about hackathons a little bit later as well. Another example was the use case centering around 3D printing. So 3D printers, despite being, highly praised to revolutionize many manufacturing challenges, particularly around complex parts and customizable parts, low-cost 3D printers, they are not very well fitted to operate within industrial environment, unfortunately. So this particular one that we've been looking at had poor sensing capabilities on board. And what we wanted to be able to do is to offer this to an SME so that they could make use of 3D printing capabilities, but what they needed to do was additional sensing capability for this particular use case. So we retrofitted some additional sensing capability that allowed us to do vibration monitoring, and that was required to improve the quality control of the 3D printer. So we then used a cloud-based analytics platform to do quality analysis so that we could relate that back to this sensor settings, the 3D printer settings, and then we could use it to control quality outcomes. A third example is a very simple really development of a QR code-based inventory checking system. And this was built in the lab and then deployed in a number of companies. So what this is that it's about detecting parts that arrive into a warehouse to track locations in which parts are stored. potentially using a QR code analysis and a camera connected to a Raspberry Pi system. So the idea is that when an item arrives, it gets scanned, and then the system recommends where the item should be stored based on location availability. And you can then subsequently, of course, search through those parts and trace where they are in the operation. So it's an example of a simple system that can be used to improve inventory planning. Here's another simple system that's unfortunately not very prevalent in SME companies, even though it's crucial, really. So it's a means of converting job cards into digital job cards, which literally just describes the particular components that are required for a job, such as an assembly, assembly components, and resources that are necessary to complete that particular task. And it captures the requirements and specifications for that job. For example, tolerance levels and so on. It then monitors how the job has been evolving and records the different activities as they proceed. So this then helps companies to trace what's happening on the shop floor. It prevents overproduction and enables on-time production, helping companies plan really better for inventory and different resources that are required for future planning. So it's really key to manufacturing, and this system that was developed, that it can be used on a tablet or a phone rather than a piece of paper. So so then it could, then we avoid errors, missing information, and so on the shop floor. And all these examples that I have given you so far, the components of the solutions, they add up to less than £100. So we really were trying to come up with ways to develop cheap solutions fast. And on the supply chain side of things, which my particular group has been looking at, we have trialed low-cost solutions that allowed for data sharing, particularly on ad hoc supply chain formations. And that was because data sharing between supply organizations is really key in order to understand how inventory, how material is flowing through the system. But SMEs, which form the backbone of UK supply chains, they do not really have the means of developing costly data tracking solutions, and the ones that exist on the market, they really need a long time to implement, and they only are worth it if the relationships that are contractually set up in a supply chain are long-term enough. So what we found here was that automation is key, because then we avoid manual setup costs. And what we have been looking at was the use of autonomous data sharing technologies such as agent-based systems to be a very interesting area that is fostering hopefully some future emerging research. And also agents coupled with blockchains, the move to decentralization, using, for instance, search engines to allow companies to search one another and set up ad hoc supply chains. Those were kind of new technologies that are coming into play in this area, and they are at the same time low cost. So another idea that we had, which was separate to the autonomous data sharing, was around creating custom data integration platforms using the cloud, so that they could be securely set up and act as a single source of up-to-date information. We trialed these solutions in a number of different use cases, including port logistics and Felixstowe, and showed that how timely information can allow queue times to reduce, for example, as logistics companies send trucks at the right time to avoid queuing. So when we examined which barriers we have addressed mostly within this trend, it's a diverse and rich set. And primarily, I'd say collaboration and business case for IoT, because many of these projects wouldn't have been possible without pitching. And the collaborations are long lasting. So we have several proposals and patents in the pipeline, as well as a startup company So please do get in touch with us if you're interested in any of these solutions. So just the final slide, I guess, in terms of the key conclusions. In summary, we demonstrated here how SMEs can get access to low-cost digital solutions for manufacturing and have done various outreach activities. And one of the great benefits that we have seen was to allow students to get involved in developing manufacturing solutions in the form of hackathons. And we brought together computer science students with manufacturing engineering students, as well as industrialists who posed them challenges. That really led to innovative, interesting applications and will continue to do so. And we hope that we have created a sustainable ecosystem of various different stakeholders with whom we will continue engaging with in the future. So in going forward, the key considerations, I guess, in this strand will be around, who will pay, who will be responsible for the platforms that are developed, which will, I think, become a decisive factor in the future. Decentralized AI and autonomous approaches, they seem to become an emerging force in the future, but trust in these needs to be developed. Yeah, so I guess these are my general conclusions. I hope I haven't gone over time, but I hope you enjoyed a whistle-stop tour of low-cost automation and what it can do. And we are looking to expand on these lessons with more projects in the future. So please do get in touch, and may I just take the opportunity to thank again to all the researchers, operations managers, and PIs that have been involved in the manufacturing strand of Pitchin. Thank you.
Okay, thank you, Alexandra. I think next up we have Boyang. So Boyang, if you're ready to go, who's going to be talking about his work at Tinsley Bridge, I think. Yes, that's right.
Hi everyone, I'm Boyang Song. I'm a research associate for the University of Sheffield, for the research team led by Professor Ash Tiwari. I'm glad to have the opportunity to introduce our project about how to develop and apply industrial IoT and predictive maintenance for a legacy manufacturing system. Before I get into the details, I would like to thank Pitchin for sponsoring our project. This work was collaborated with multiple academic and industry partners. In the research part, with the Sheffield team developed the IoT system. Worked together with Cambridge team, we developed and validated the deep learning method to analyze manufacturing process and quality data. Our industry partner, Tinsley Bridge, is a prestige manufacturer in Sheffield steel industry, founded since 1850. Tinsley Bridge have provided a case study of legacy manufacturing facility and help us test our developed IoT system on the shop floor. Siemens was also supporting us by providing the access to the latest IoT and industry edge platforms. We are targeting two challenges here. The first is about how to digitalize manufacturing process for a legacy system, how to capture the data for the manufacturing shop floor. The second is about how to process the captured data with machine learning or deep learning methods to improve the manufacturing operation performance, such as quality control or equipment maintenance. Our project in general can be summarized in 4 stages. The first stage is about understanding the manufacturing system, which is an encoding facility built 20 years ago. As you can see for the photos, that before our project, this manufacturing process was measured by the mechanical gauges. The operator needs to go to every checkpoint, manually read the gauges, and record the measurement on the paper, then type them into Excel sheet later. In the second stage, after we figure out the priority of the checkpoint, we have tested a range of IoT devices and installed them with a digital sensor on the shop floor. The third stage is about the development of the IoT software system. We have tested the IoT system developed by Siemens, which is called Matchfield. It's designed to connect the machines for the shop floor to the cloud. We also developed and deployed the on-premises system, which keep all of the manufacturing data within the factory. As a result, we can monitor not only the condition of our targeted manufacturing process and machines, but also the performance of our IoT hardware and software. In the last stage, we have developed a deep learning model trained with the captured data. The trained deep learning model can predict the critical process conditions, also the health indicator of the equipment. These prediction results can better instruct the maintenance activities, thus reduce unplanned downtime. In our journey, we have studied with general IoT devices and sensors. Then we have realized many challenges to keep them in the HEIs manufacturing environment. For example, Wi-Fi may not work around heavy electric machines because of the signal interference, so we cannot connect this device with wireless connection. Some sensors may not last long with the oil and dust. General IoT devices can be difficult to connect with other industrial devices due to a different power supply and communication standards. Then, we have gradually updated the general IoT devices to the industrialized IoT devices, also updated the sensor to more advanced industrial sensors. This is a glance about the manufacturing environment in our case study, give you some insight about various IoT devices and sensors we have deployed on the shop floor, what is the cost of the hardware, and what kind of data we are collecting for the shop floor. One achievement for our project that we have published the data we collect for this project on Kaggle. The dataset is nominalized in order to avoid the exploit of sensitive business information. At the same time, it's fully functional to train a machine learning or deep learning model. The dataset has two parts. One is 7 years manual inspection record of key process measurement in a low sample rate, which is 3 times per day. The other part is same type of measurement collected by digital sensors and the industrial IoT system within a short period and relatively higher sample rate, which is the 1 data point per second. We have provided detailed instruction of the dataset on Kaggle repository and hope more researchers can use this dataset to understand better about the manufacturing process data and develop more and better methods to solve manufacturing problems. We have developed deep learning method to predict the process condition for the following 24-hour period based on past 5 days information. We are targeting to solve the common data problems for manufacturing use cases. That you may have lots of low-quality data which cannot provide you required details, and you don't have enough time to collect enough quantity of high-quality data during the short period of the project. We have used deep transfer learning method to overcome this challenge. But you can see the figures in the middle of this slide. The red lines are the predictions. The green lines are the actual process condition. The left and the middle columns are trained by only manual inspection dataset or the IoT dataset. The errors are quite big. After we apply the transfer learning for both datasets, we can predict process condition in much accurate result. Cambridge team has also developed a demo, which is agent-based method to represent a manufacturing system involved with multiple machines. The condition of the machines varies over time. Then BASIM autoencoder method is developed to quantify the uncertainty of condition of the machines and the quality of the product. The demo has been published on the GitHub. You can find more details there. There are lots of lessons learned for this project. The most significant challenge we have found within the project is that people from different backgrounds are speaking very different language. For example, manufacturing operators, automation control engineers, computer science researchers, they may speak totally different terminology and have a different view on the very similar thing. How to use the right language to communicate between manufacturing stakeholders and the research team is very important. The other barrier, maybe is also related to this one, is a barrier of domain knowledge. It's hard for pure computer science people to understand factory operation, manufacturing IT and OT infrastructure in a short time. It's the same to let pure manufacturing people to have a good understanding of deep learning in short time. Very few people have the cross-domain understanding. So we probably should to work together with an interdisciplinary team or train a talent who can equip multiple domain knowledge. I think it's challenging to train this kind of talent in our current education system. For the next step, we are developing a desktop-sized demonstration platform, which will represent our developed IoT and AI application for manufacturing use cases, introduce the end-to-end workflow of data collection, data analysis, and result reporting to instruct manufacturing operations. For my research, I wish to continue investigating how to decentralize machine learning or deep learning on industrial edge devices. At the same time, enhance the cybersecurity when connecting IoT system to the industrial control system. Thanks a lot for listening. Welcome to check our published data report on cargo and read our research paper later. Thank you.
Okay, thank you, Yang. Oktay, are you ready to go?
Yes.
Okay.
So let me share my screen. I hope you're able to see, right?
Yep.
Okay, perfect. So, okay, hi everyone again. I'm Oktay, I think I am. Today I will be talking about automated network evaluation in dense urban settings. So let's start with the problem. So the problem is the rapid global urbanization and increasing population and the ever-changing urban landscape. This, of course, inevitably affects so many things around us, but most notably the wireless networks. Because in cities where tall structures are clustered together, this is the direct impact of urbanization. The signals are not blocked by concrete and metal, but they also collide with each other in the canyons between the tall buildings, which weakens the signals. And when wireless signals pass through objects, these buildings, they become weaker due to the reflections of or the absorptions by this object, so which refers to building loss. And different materials exhibit different building loss at different frequencies. Besides, the wire mesh in the buildings also acts as a Faraday cage, which prevents RF signals to pass through. So while these are happening, one problem is getting intensified even more, which is the RF spectrum, which is already scarce, and we are putting more and more devices, adding more devices to that scarce spectrum, and we are actually giving more and more critical tasks to these devices. So this definitely poses a problem. So because we do not actually treat the wireless infrastructure as we do with the grid infrastructure like gas, electricity, or like, I don't know, telephone lines. So, and we have to understand what happens when we, for example, structure a building just by a base station. So how we disrupt the RF signals. So this project is about that actually. And what we need to do is we need to measure and interpret the use of RF spectrum, the current status of the wireless infrastructure, cellular connectivity in mobile, cellular, Wi-Fi, and emerging networks, devices that will be added and operating on this based on these technologies. So, and based on this, we need to understand how the ever-changing urban landscape is affecting the operation and coverage, penetration of the RF signals. So, and the idea is again modeling and mapping the current infrastructure, current status of this, understand the current status of the system, so that maintain extensive coverage, build a reliable LoRaWAN gateway infrastructure to provide IoT connectivity across cities, and based on experimental surveys and also simulations, optimize the wireless infrastructure by relocating the wireless equipment or maybe increasing the numbers. So we started with the LoRaWAN gateway deployment. So this map shows the 8 gateways we have right now in Sheffield. These belong to us, but there are also ones with the city council, and also the ones belong to companies, individuals. So I can say that we have a very well actually structured gateway infrastructure across the city region. So this shows just a couple of examples. The gateways we have on IKEA and KIX building of the university. So we deploy different gateways, different models with different specifications, antenna configurations to understand which gateway performs better in dense urban environments, so that we can optimize the infrastructure. So this shows the performance progress, the surveying work we did. And of course, this is even better now by June 2021. So what we have is now almost all full coverage across the city region. So we provided a platform for anybody actually in Sheffield, allowing them to build their own IoT application, because we provided an IoT coverage in the whole, for the whole city. So, and Sheffield is one of the best places in the UK in terms of IoT coverage and connectivity, thanks to this Pigeon project. So, and how did we do this surveying work? We used two different settings, the walk, drive test, and walk test experiments. So for drive test, we used an observatory-owned electric vehicle, which includes an autonomous mobile network scanner, which is used for walk test experiment as well, in addition to the GPS trackers, which were to understand the LoRaWAN connectivity. So, and this shows the results in the surveying work. So on the right-hand side, you see we collected actually 20,000 data points, which gave us a highly granular IoT coverage map data. So here, as the close-up shows the citrate level coverage map. So this is highly useful to understand where we have the coverage, how we can actually provide access and connectivity to IoT applications. So, and due to pandemic, we had to change a bit. So we used a ray tracing based 3D network planning software to model buildings in 3D and also their surroundings like the city in 3D. So, and so that we actually analyzed indoor to outdoor and outdoor to indoor penetration analysis. And that was quite useful to understand how the urban landscape is affecting the wireless propagation, because we were able to actually build buildings, relocate them or remove them, add them. So, and which allowed us to analyze wireless propagation in indoor and outdoor. So the results, we had a thorough analysis of scientific literature, the factors disregarded in literature, we highlighted them, and we provide a highly granular network coverage map with these experiments we did. And with the surveys, based on experiment and the simulations, we identified the causes of fading, the material impact, building loss, and also the landscape, the impact of landscape on the wireless network performance. So at the end, we provided potential solutions to offer reliability and efficiency in the city. So by extending this work, I mean, we acquired an additional funding where we focused on indoor modeling particularly. And the lessons learned is empirical data collection. We collected enough data to understand anything really going around the buildings and in the city in terms of wireless infrastructure. So 3D modeling and simulation, we supported our experimental results with the simulations using this ray tracing based software. And by using both, we provided a better coverage and optimized the wireless infrastructure, provided guidance for the stakeholders. And we provided our results in so many events, and one of them was quite useful because now we are collaborating with an industrial partner called Connexin on the extension of this project. We're working with our colleagues in the Tripoli department again to extend this project in the 11 bits. And we already have a journal paper, and we have one conference paper is about to be submitted, and hoping that we will extend this project to a wider audience. So the next steps, currently we are working with Barnes at the MCO2 for 3D modeling of indoors and to understand actually the wireless network performance in indoors. And we will work with ICARE, University's ICARE Center for Material Characterization Analysis. And we will extend this work to pick district national park to provide IoT coverage in rural areas for special healthcare applications. And these are the potential topics that we determined. So if you're working on any, please get in touch. We are more than happy to work with you on the extension of this work. So I think that's all. And thank you very much. If you have any questions, please put them in the chat and I will try to answer.
Okay, thank you, Oktay. That's great. Next up, Yitam. Yitam, are you there?
Yep, I'm here. How are you?
Okay, go for it. Go for it. Take it away.
Just give me a sec here while I get my talk running. Okay. So I'm probably, apologies ahead of time, because I'll probably provide probably the least technical talk here, because I'm not actually, I'm a ecosystem scientist, so, and I'm relatively new to the world of IoT and so forth. So I became involved in this project with Phil James and folks at the Newcastle Urban Observatory about just over a year ago, when there was some interest in trying to explore how IoT and you know, network sensors and so forth could provide useful data and applications to you know, ecological monitoring, environmental monitoring, use by farmers, land managers, and so forth. And hold on, let me scroll through. And I think in terms of the wider context, I think what has been noted on a number of occasions is that outside of urban areas where it seems like there's been sort of better uptake, you know, within the urban context, industrial context, there's good uptake of, you know, or appreciation that these kinds of technologies could be useful. There's been a lot less uptake in rural areas, particularly in sectors such as farming, tourism, biodiversity management, and conservation, and so forth. However, I think there's increasing sort of realization that use of these technologies could be especially useful for things like disaster management, for us, you know, flood monitoring, fire detection, and so forth, monitoring spreads of agricultural pests or pathogens, these kinds of applications. But so far, there have not been, you know, there's not been as much adoption from these different sectors that function in rural environments. So what we were interested in doing was working on a number of test sites or case studies in a sort of participatory approach with stakeholders to demonstrate the utility of these systems and to explore what the potential limitations might be, or what the needs might be, and so forth. So what we did is, you know, again, I sort of mentioned some of these points. We wanted to showcase how some of these IoT systems could be beneficial for environmental and land management practices. We have a long-term ambition at Newcastle to set up what we're calling a rural observatory, or a way of using you know, a range of different sensors, as well as working in sort of a multidisciplinary framework with different kinds of researchers to try and understand, take a systems perspective of rural environments, and trying to use a systems perspective that includes socioeconomic components to try and understand how we can improve the sustainability of existing practices. And we identified quite quickly, identified three sort of key sort of stakeholders that we could work with. One of them was Northumberland National Parks. The other was Heppel Estate, which is a farmers who are a farming operation who are quite keen on doing some rewilding, and Newcastle University Farms, who are sort of operating as we have these commercially functioning farms that are quite interested in working with our researchers to improve on sort of farming innovations and so forth. Just to give you an idea of where these places are, the Northumbria National Park Authority site is here, and it was a study to look at tourist footfall. Heppel Estate is located further north, and this is the sort of the rewilding location, and Nafferton Farm, which is the Newcastle University farm where we were interested in setting up some environmental monitoring. It's located here in the bottom right of the screen. So, you know, a little bit west of the city. And in terms of what we did, I mean, we only had 1 year to roll this out, and it was disrupted by COVID and so forth. So, you know, not as many results as some of other colleagues have been able to show today, but just to give you a sense of where we're at the moment, we were able to set up a number of people counters along the Hadrian's Wall sort of site to try and understand use of that that area by tourists and visitors and so forth. We've done a lot of work, actually probably the majority of our work has been at Heppel Estate, where we've got a number of different sensor networks set up, some for monitoring environmental conditions, so microclimate and so forth. We have a number of sensors for tracking animal activity and behavior. So for instance, what I'll show you in a second is we've got a number of GPS collars for tracking the movement and behavior these semi-wild ponies, and we're going to set up some collars to track livestock, cattle in this case. And we've recently acquired several sensors to look at pollinator activity. And some of our team have gotten training to deploy those. So you know, linking into concerns about pollinator declines and so forth. We've also set up some water quality sensors at Nafferton Farm, because clearly there's concerns about sort of effluent and transfer of potential pollutants from, you know, sort of downstream from our farming operations. And so that's been put in place. Just to give you sort of a couple of highlights from the data, not too much, like I say, because a lot of this work is current and ongoing. This is some of the information from the livestock tracking, just some data from the livestock tracking work, where we're able to look at how these animals were moving through the landscape. And we're finding that, and in this case, the positive values indicate areas that the animals tend to frequent, whereas the negative values are areas that they pretty much don't go to at all. And in this case, we found that these animals were clumping around certain areas within the landscape and tending to not visit at all certain other components of the landscape. And that information is really useful from a management perspective, as well as from sort of a basic science sort of animal behavior perspective, because it enables us to ask questions about what could be driving movement and distribution of those animals. Is it resources? Is it climatic conditions? You know, there's obviously some variability across this ecosystem in terms of temperature, sun exposure, and so forth, as well as differences in vegetation. So it enables us to sort of probe those questions later on. And it's a useful tool for managers to try and understand which parts of the landscape may be most heavily utilized by livestock. We've been developing some of these tools for our stakeholders to use. So for instance, there's this sort of almost real-time visualization of where the animals are within the study landscape. And we've been working with our stakeholders to sort of visualize the data in ways that, you know, they find useful. I won't have time to outline all of them here today, but I'm happy to discuss them with you later. So in terms of what we've learned, I think, you know, it's really clear, and, you know, maybe this is a bit of a no-brainer that, you know, IoT networks can play a really useful role. But I think what we found out that was quite interesting is that, you know, we're very far away from it being sort of plug and play, right? So there's going to be a need for ongoing engagement with a research community. We can't simply sort of deploy these sensors and let the stakeholders use them. Even if we do develop some nice interfaces for them to work with the data, there's still a need for us, for folks with a skill set that can help them maintain that information, troubleshoot when problems arise. And actually, in some cases, depending on how complex the data is, there may be still need for involvement from the data interpretation angle of things. I think there's quite an interesting story here in terms of understanding how to develop effective collaborations with stakeholders, because as I said, we were working in what was effectively sort of a participatory or co-innovation, co-development sort of system. And I think, you know, there's probably a master's project or a PhD here for ethnographers, budding ethnographers, to try and understand that interaction. And the other thing too is, I think something to note is that even though, you know, some of these IoT sensors have become increasingly affordable, a lot of them aren't really fit for purpose or use in these environmental settings, because they turn over pretty rapidly, because they just don't hold up to weather and rainfall and changes in temperature or freezing events and so forth. And we have spent quite a lot of time sending folks out to the field to recover, repair, and replace busted sensors, basically. So I think, you know, quite a lot of thought needs to be put into how to adapt the hardware, the initial hardware that you get, to make sure that it continues to deliver useful information and functions to spec, basically. And with that, I'm going to wrap it up and say thank you, and happy to take any questions in the chat.
Okay, thanks very much indeed. And our last speaker today is Belinda Lennox. Take it away, Belinda.
Hi, good morning, everyone. And as they say, now for something completely different. And I accept the challenge for the least technical talk of the morning. I'm a psychiatrist. I'm a clinician. I'm also an academic down in Oxford. And I'm telling you about, I think, a really exciting project for our world, which was made possible by Pitch In. So first of all, I'll tell you the problem we're trying to address. So I see people with serious mental illness, so things like schizophrenia, bipolar disorder, which are actually really common, affect 500,000 people in this country. Whilst their management and treatment is under the domain of mental health services, in the UK, mental health services are completely divided physically, culturally, anthropologically from physical health services. So the general hospitals are in different places. And the physical health care for people with mental illness is poor. And this is demonstrated here, just showing your risk of death if you have a diagnosis of schizophrenia is about 15 years lower than your peer in the population. And you die from largely preventable illnesses. You die from cardiovascular disease or you die from lung cancer. So things that there are very good prevention programs and screening programs for helping other people detect these disorders early and put interventions in place, but they just don't work for people with mental illness. And it's a system problem, essentially. And so this is just to demonstrate, so we're meant to be monitoring physical health in people with mental illness. We're meant to do it on an annual basis. And it's meant to be shared between the mental health service and the GP, who has responsibility for physical health care for people in the community outside of hospitals. So at the moment, what happens with people under my service is you identify they need a physical health check. You might have a mental health worker that can take blood from the patient, in which case, you know, that's pretty lucky. They'll take the blood sample, but then they'll send it off into the ether. They'll send it to the lab over at the general hospital site, and then the lab will process it and send back a bit of paper with the results on that get filed into a system, by which time the patient has gone off and got on with their life. And you may or may not pick up on the result, and then you have to make another appointment to meet up with a person and tell them what the results are and what needs to happen with that. If you don't have someone in the mental health service that can take blood, then you tell the patient to go to their GP to have their blood taken, which may or may not happen. And again, the GP takes the blood sample and the blood result goes back to the GP. And then the GP actually faxes, we actually use faxes still, to the mental health services with the blood result. So you can see it's a really convoluted, useless process, with the end result is that most people don't get physical health checks in a timely way. So our solution that we have introduced is a point of care testing machine that is a box that you take to the patient's side, you do a finger prick of blood, and you test it, and in a couple of minutes later you get the result there and then. So you get to say what the cholesterol is, or what the HbA1c, which is a measure of diabetes, is. And then, you know, with the patient in front of you, you can say, your cholesterol is high, you know, what are we going to do about it? Let's look at lifestyle interventions, let's look at, you know, exercise, all the rest of it, you know, alongside the patient. So it's a sort of simple, direct solution, you know, that seemed to make sense. So our question was for our project was, you know, can the point of care testing machines improve the uptake of physical health checks? And of course, we needed lots of different partners. We needed the provider of the point of care testing machine. And actually an important bit of work that went on beforehand was actually to evaluate, there's quite a few of these machines and they're not all actually very good. So they needed to be reliable, they needed to be accurate. So we did that bit of work beforehand. We worked with system integration experts, because a key part of this was the Internet of Things capability to actually get the connectivity from the point of care machine directly into the electronic patient records. So we worked with partners to enable that, both across the acute hospital and across the mental health trust. And we worked with another bit of system, the NIHR, the National Institute of Health Research, who have a medtech in vitro diagnostics cooperative. And they really importantly give us expertise in both the quantitative and the qualitative evaluation of this machine, to make sure it didn't just sort of sit on a shelf and become a dusty bit of technology. So we introduced the machine into one service over a 6-month period, and we also collected data on a parallel service in a neighbouring county which didn't have this machine. And we showed that over the 6-month period of time, we increased the completion of the blood tests by, up to nearly over half the caseload were able to have a blood test. And in the comparable team in the black there, it remained at about under 20% of the caseload had blood tests. And also, importantly, the blood tests are only one part of the evaluation, the physical health check. So in the couple of minutes you're waiting for the test to come back, you can measure someone's BMI and talk about smoking cessation and all the rest of it. So actually the rate of completion of all the tests went up as well. Importantly, we asked people why it worked, and in places where the clinicians didn't use it, why it didn't work. Overwhelmingly, the patients liked it. It reduced their anxiety. They don't like going to GP surgeries. It's hard to make an appointment, especially nowadays. And they found the integration of the physical and mental stuff in one place just made sense. The staff that used it found that the machine was easy and it increased client engagement. But there's another story to be told for the staff that didn't use it. Actually, it threatened their professional identities. They didn't really think it was part of their job, and they were a bit worried about, techie stuff. So it is important, the training and the support for staff actually was an important aspect to make this successful. So the key lessons that I suppose I take away from this project really is that the qualitative stuff, actually asking people how it was for them, was really vital to understand the barriers to implementation. And these rare folk, these boundary spanners, the guy Mike Dennis, who works for Acrivia Health, who's worked in mental health systems and electronic patient records for 30 years, he was just vital for connecting systems together and making the electronic patient records link up, which sounds like a really small thing, but actually in my world, it makes a big difference. So the next steps are also quite exciting. So we have been funded by the NHS to broaden this pilot out across the whole of the southeast of England. We're exploring other point of care devices like this little gadgety iPhone thing for measuring your ECG, and NHSX, which is the sort of new body which brings together Department of Health and Social Care and the NHS for looking at digital technology, has adopted physical health checks in mental illness as an exemplar project for this year. So it's a sort of must-do for the whole of the NHS across 2021. So we're suddenly in great demand, basically. And I just want to say thank you to Pitch In, because it was the integration across the systems. Actually, no one has managed to do very well up to now. And it was the time-focused funding that actually made it happen. So you can instantly see the value of using these machines, and it's been adopted into clinical practice, and it's now routine. And that really wouldn't have been achieved without you. So thank you.
Okay, thanks, that's great. Can I thank all the speakers today, those from within IoT, as we normally interpret it, but particularly actually those from outside the IoT fraternity. So because it always pays to start with the problem and let the solution follow. And I think that's what we've seen from Yitante and Linda Lennox, particularly today. So thank you for attending today. I hope you've enjoyed it. If you have any further questions, put them in the chat. I'm sure the administration people will be reminding me, they are indeed, that the conference is not over. All we're getting now is, we're bang on time incidentally, so thank you to all the speakers. We come back at 11:20, so we're having a half an hour break. We'll continue with some more project highlights, a talk from the KTN and on IoT and 5G, and then we'll be having a session on where next, so the KTN and ourselves are going to have different variants of where next, and then we're going to have a question and answer session, dynamic and interactive with the audience. So please do come back at 11:20. We'll be ready and waiting to go, but do have a good rest. Okay.